From this equation, notice that so we have the acceleration term, the linear restoring force term, and then we have a nonlinear restoring force term. So if you were to write the force for that equation, the force for that equation would be the term kx, right, minus kx, and then there would be a term alpha x cube, right? So that would be your the force acting on a mass. So you can imagine a spring that is nonlinear somehow acting on a mass m, and the force of the spring on that mass has two components: a linear Hookean, a linear Hookean term, and we were talking about you. And then a nonlinear term, which is obviously non-Hookean. You know, Hooke was a contemporary of Newton. You know that? They were contemporaries. They were actually, or in Hooke's mind, they were scientific rivals. In Hooke's mind, right?
Newton was crazy also.
Huh? Of course, but he was a genius, right? I mean, so we will dispense any problems, any psychological problems he had, because he's probably the smartest person in the history of humanity. Okay, probably above Einstein.
That's the reason that Einstein said, "Sorry, Newton." That's right.
Yeah, he stood on the shoulder of Newton. So, but Hooke was contemporary. Actually, Hooke was developing at the same time as Newton was some theory of gravitation, but Newton had it right, and Hooke was in some ways very antagonistic to anything that Newton had to develop. Who was the astronomer? I think it was Huxley. I think that prompted Newton to publish his theory of gravitation, because he had it ready for long time, for several years already, and he just pulled it from the drawer to show the answers. So the Hooke is famous, but for this term, okay, for the Hookean force. I don't think there is any other theory for which is known, but that. But so we have in the force acting on this mass, we have not only the Hookean term, but the nonlinear term. And depending on alpha, the sign of alpha, this can be a stiff spring that gets stiffer with amplitude, or a more compliant spring that gets more compliant with amplitude. You know what I'm saying? So it gets softer. If alpha is positive, then the spring would get softer with amplitude. The force acting on the mass would not increase. Well, rather, it would continue to increase, but it would not be the rate of increase of the force with amplitude would be negative in the following sense. So if we plot force as a function of displacement, Hooke's law is this straight line. Okay. Then when we incorporate this term here with alpha negative, the force goes like that. The force gets softer, increasing the displacement makes the force, or rather the rate of change of the increasing force less.
But with alpha,
this would be with alpha positive, which is called the softening case, right? A soft spring would behave like that. A hard spring would be alpha negative. So the spring would get stiffer with amplitude. So the negative view would be like this. Okay, so as you increase, small increases on the amplitude give rise to large increases on the force. So it's a spring that becomes stiffer with amplitude. So those are the two extremes, or the two possibilities for alpha. So this is negative alpha, that is positive alpha. So the problem we are solving here is takes into account the two signs, the two possibilities, alpha positive or alpha negative. So what we did yesterday was to go beyond the method of iterations and consider the fact that when we have an oscillator, nonlinear oscillator, that is undergoing nonlinear oscillations, the period of oscillation depends on amplitude. In the case of, if this term is 0, the period of oscillation only depends on the spring constant and on the mass, right? It's the square root of k over m. But when we have nonlinearities, the period of oscillation depends not only on the stiffness of the spring and the mass that is attached to the spring, but also depends on the amplitude of oscillation. So we set that particular distinction or that particular concept, we set it here in the solution. We say the frequency omega at which this guy oscillates on account of nonlinearities is not omega naught. It's some different frequency omega yet to be determined, and to be determined by balancing harmonics. And so we're saying the solution is periodic. It's a periodic solution, but it's not a harmonic solution. So we are going to include harmonic terms in the solution. We have the term that goes as cosine omega t, and then because of the nonlinearity, and we discovered that to be the case with our iteration process, because of this particular nonlinearity, the cubic nonlinearity, the only harmonics that can be present are the odd harmonics. So we have cosine omega t, cosine 3 omega t, 5 omega t, and so on and so forth. We are saying that we are considering weakly nonlinear behavior, okay? In the sense that each harmonic term, each higher harmonic term gets a smaller and smaller amplitude. It's smaller in strength. So this guy would be smaller than that guy, or rather the amplitude of this harmonic term would be smaller than the amplitude of the fundamental term. So we are making that statement that way. And we are also making another statement. We are saying, in general, we are considering this problem to be a weakly nonlinear problem. How do we quantify that? By comparing this with that, or comparing in the force by comparing the Hookean term with the nonlinear term. By saying that we are not exploring the full range of values of x, but only a range of values for which nonlinearities are being probed by the system, but they are not significantly large. Okay, so we are moving off the Hookean regime, but not too far off. And how do we make that statement? We say, well, we compare the linear term with the nonlinear term. We're saying this term is bigger than that term, so that the force graph is not exploring the full range of values of amplitude. So when we compare this term with that term, we can make this statement that omega naught squared is much bigger than the magnitude of alpha, because alpha can be positive or negative, the magnitude of alpha times the amplitude squared. So this is a small amplitude approximation. We are not saying it's infinitesimally small, we are just saying it's small. So we are still going to probe the nonlinear behavior, but we are not going to go to the full nonlinear behavior. Notice that if we are dealing with a softening case, as the amplitude increases beyond the weakly nonlinear region, notice that the force eventually goes to 0, right? The force vanishes at some amplitude. if alpha is positive. It never vanishes if alpha is negative. So we don't want to go there. We just want to do the weakly nonlinear cases. So we call this the softening case, and that is the hardening case. Because it looks like the spring gets softer with amplitude for the softening case, and it gets hard with amplitude with the hardening case. Yes?
So in a small amplitudes, we always have both the linear part and the nonlinear.
Yes, yes.
Yesterday you told that in the mass of the spring, in small amplitudes, we don't have the linear part. It vanishes.
Oh, in the homework problem that you're solving, you're gonna find for that homework problem, if the springs are unstretched, in that configuration, right? These are linear springs. If you were to move in this direction, you would have only linear oscillations, where the frequency of oscillation is determined by the spring constants, which we're saying they are the same, right? And so the frequency of oscillation of this system of mass m and spring k would be simply what? 2k over m, the square root of 2k over m, right? That would be omega naught. If you have that oscillation, that would be a linear system. Now, in the homework problem, I'm asking you to not consider this motion, but to consider motion along that direction. If the springs are unstretched, if you don't pre-stretch the springs, then this oscillation would not have that term. Okay, it would be
for small amplitude.
Even the infinitesimally small amplitude would not give you a linear term in the force as a function of amplitude, as a function of displacement. You don't have linear dependence. So you need to stretch the springs to get that term to occur. Okay? So you're going to see that as you work out the solution. That as you expand about small amplitude oscillations, the unstretched case has no linear term. The stretched case does. Okay. All right. So these are the basic working assumptions that we have. We are looking at harmonic solutions where the higher harmonics get to contribute less and less as the harmonic order increases, and where we are considering a small amplitude of oscillations which can be quantified this way by making that statement. Omega squared is much bigger than the modulus of alpha times a squared. So what we did yesterday was to incorporate that harmonic solution. Okay? On the right-hand side, on the left-hand side, we have the derivative, the second derivative. These are all these terms. Then we have omega squared times x, which is right there. And then we have on the right-hand side alpha times x cubed, which is that. And then what we do in the harmonic balance problem is to balance equal terms. Cosine omega t, cosine omega t, cosine 3 omega t, cosine 3 omega t, and so on and so forth. And so we are looking, there is a cosine omega t term right here. There is a cosine omega t term right there. So we collect them. I just collected them right here. And then that's from the left-hand side of the equation. Then from the right-hand side of the equation, there is going to be a cosine omega t term that comes by cubing this guy. The cube of cosine omega t has a term that goes as cosine omega t, and has a term that goes as cosine 3 omega t. And then I'm going to have products of the square of these with that, say. That is also going to give me a cosine omega t term dependence. But that goes as the product of a squared times b. And a squared times b, a term that goes as a squared times b is smaller than the term that goes as a cube, right? Because we are comparing, say, a cube is the same thing as a squared. and we are comparing a cubed with a squared b. So essentially we are comparing b with a, right? And b is much smaller than a, so we can drop that term. So far so good. Is this clear? It's clear? Yeah? Oscar?
Yes.
You, okay. You look puzzled? Okay. So that's why I'm writing here. I'm picking up the contribution from this guy that goes as cosine omega t. So cosine cube of omega t is equal to 3/4 of cosine omega t plus 1/4 of cosine 3 omega t. So I'm picking the contribution that goes as cosine omega t from there. And then plus higher order terms that are smaller that I can just neglect because b is much smaller than a. So this was the result that we got yesterday. If you do the same problem for the cosine 3 omega t terms, so you have that guy on the left-hand side, which I collected them right here. And then on the right-hand side, you would have the cube of cosine omega t has a cosine 3 omega t dependence, which is 1/4 cosine 3 omega t. So that's where this guy comes, plus higher order terms that I can neglect. So this result gives me two particular insights. One is how omega, the frequency of oscillation of this nonlinear oscillator, depends on amplitude. And it also tells me how at least the third harmonic amplitude depends on the first harmonic amplitude. How B depends on A. Okay, so I have, by matching harmonics, I can do that. I could continue this process with the higher harmonics, but we have a lot of information right here to process, and it's good enough to do the full weekly nonlinear analysis. So let me first take this guy. So I'm gonna neglect this contribution altogether, and I'm gonna just make the statement that the frequency is related to amplitude through this expression. Notice that amplitude here drops out, and this is a square. So we have that omega square from there. Omega square is equal to omega naught square minus 3/4 of alpha a square. Okay? So that result tells us that the frequency of oscillation decreases with increasing amplitude if alpha is positive, and the frequency of oscillation increases with increasing amplitude if alpha is negative. So in the softening case, alpha positive, the frequency decreases. In the hardening case, the frequency increases. So if you were to do that, make some kind of plot representation of that. If this is amplitude, and say this is omega naught, that is the linear behavior, then this relationship, so if the problem were linear, regardless of the amplitude, you would always have the same frequency. But because of nonlinearity, you have that for the hardening case, and this for the softening case. Okay? Now notice that if we are bold to extrapolate this result, okay, let's do that. Let's be really bold and extrapolate this particular result to the case where the frequency becomes 0 for the softening case. So this is the softening case. There is an amplitude, right? There is going to be an amplitude for which omega is 0. The maximum possible amplitude would give you an omega equals 0. that means the period of oscillation is infinite. In the case of the pendulum, right, that will correspond to the case where the pendulum goes to the top. Okay, it takes, for the pendulum to go to the top, for a free pendulum to go to the top, it takes an infinite amount of time. Okay, that period of oscillation is infinite. Okay, for a pendulum. So let's take this approximate result and see where are we in our picture. So we have the maximum amplitude right there for the softening case would correspond, from according to this expression, to the problem where, or to the case where omega goes to 0. That's the maximum possible amplitude. Beyond that, for larger amplitude, we have an imaginary frequency. Then we don't have oscillation. So we stop right there. So what is that? So omega equals 0 means that the maximum amplitude here is equal to 2 over the square root of 3 alpha. This is a positive alpha, so it's alpha times omega naught. So that is my maximum amplitude. Okay, 2 omega over 3 alpha for the softening case. Okay, so let's make sure that we clarify that this is for the softening. Okay, there is not such a result for the hardening case. The amplitude can just keep increasing, and we could keep increasing our frequency as well. But now let's compare that maximum amplitude with the physical maximum amplitude. Okay, in the softening case, the maximum amplitude would be the result of this being equal to that, when the force is 0. When the force is 0, when this term and that term are the same, right? So from the equation, the actual amplitude that we get is if we look at this guy, the maximum amplitude here would be when these two guys are the same, or when a squared is omega naught over the square root of alpha. Okay, not bad, right? That approximate result is not very distant from that exact result, right? Because we have 2 over the square root of 3. The square root of 3 is almost 2.
But the result over there, where does it come from?
From here. Right there. From saying this guy is equal to that guy. When is the force equal to 0? Right? When is the Hookean force equal to 0? So we have, rather, when is the net force equal to 0? We have the force is kx minus, or rather plus alpha x cubed. When is that force equal to 0? That force is equal to 0 when x maximum is equal to, well, there is another term here, of course. There is there should be an m right there. That is equal to 0 when we have x max is k over m alpha, and so this is omega naught, and so this is the same thing as omega naught over the square root of alpha. So this would give us the value, the maximum value that we can have in that problem right there is the value for which the force is equal to 0, which is that. Now notice that this is omega naught over the square root of alpha. The answer that we got by this approximate method, which is valid in the weakly nonlinear regime, is 2 over the square root of 3. 2 over the square root of 3 is almost 1. Okay?
It's 1.15.
Huh?
1.15.
1.15. So we are off by 15%. Okay? But I have to make sure that we are clear. That method, the method that we have developed, applies for small amplitudes. Finite but small. The problem that we have right here, or the extension that we made right here, would imply, for instance, the problem of a pendulum that goes over the top. Okay, that's not what we're envisioning with the method. So far, so good. Is this clear? Now, there is a demo. There is a demo that goes with this answer. Notice that the frequency depends on amplitude this way. By the way, I can refine this result, right? I can make a further approximation to this result. Notice that I can say, look at this. I can omega square, or rather omega square is omega naught. Omega is omega naught times 1 minus 3 alpha a square over omega naught square. Yeah, I've done nothing but just rewrote that answer. Yes, is this agree? Everybody agrees? But look what we have here. We have the ratio of alpha a squared to omega squared, which we are saying is much smaller than 1. So we can approximate this, right?
Is there a 4 there?
There is a 4, yes, I'm missing a 4. I can approximate this as omega naught times 1 minus 3 alpha a squared over 8 omega naught squared. So, okay, so this would be, in the spirit of our approximation, this would be a better answer, a better result than that one. And this is something that I like to use in later. But so this looks like omega naught square plus k a square, or kappa a square, where kappa in this case is minus 3 alpha over 8 omega naught. Okay, so the answer I have, excuse me, this is omega. The answer that I have for oscillations, for weakly nonlinear oscillations, is that the frequency of oscillation is the linear frequency plus a term that depends on amplitude square with a coefficient that depends on the nonlinearity and other physical parameters of the system. Okay, this coefficient depends only on physical parameters of the system, but has an a square dependence. Something that we're going to use in a little while. Okay, so I have a result. The frequency depends on amplitude. In the case of the pendulum, this kappa here is negative because alpha is positive for the pendulum. Actually, alpha happens to be omega square over 6, omega naught square over 6. So there is kappa is negative for the pendulum. That means for the pendulum, increasing the amplitude increases the period of oscillation, or decreases the frequency of oscillation. And we saw that. I showed you a demo yesterday. We measure the period of oscillation for a large amplitude pendulum and a smaller amplitude pendulum. And we found that it takes a longer time to undergo this large amplitude motion than the smaller amplitude motion. Okay? And remember, there was an effect yesterday that I could not control because it's very difficult, really. It's difficult to, by hand, release a pendulum, and except for now, of course, it has to fail right now. And no, it actually has a little, yeah, it has an elliptical component. It's very difficult to have a pendulum go in a plane when you release it with a hand. You see, this pendulum is not going in a plane.
Because of the difference in friction when we leave it?
Because it's going in an ellipse. This pendulum is going in an ellipse because when you release the pendulum, it's very easy to give it a little bit of a kick on one side or the other side. And so invariably, if you grab, your hands have you don't have a very accurate control on one side of your fingers with the other side of your thumbs. Say your thumbs and your index have different strengths. So invariably, you are going to give it a kick. So the actual orbit, the actual trajectory of a pendulum when you release it with the hand is an ellipse. An ellipse. Okay? So to release the pendulum on a plane, you would have to be more systematic. Say we could attach this to a string, okay? And the string is fixed, and then burn the string, and then the string would release this mass without any kick in one direction. When I release it with my hands, invariably I give it a kick this way or a kick that way. But that was an important effect. So if I take my pendulum and make it go on an elliptical trajectory, there is going to be one side of the ellipse, or there's going to be, as an ellipse, is going to have a minor axis and a major axis, right? You can imagine that the elliptical trajectory of the pendulum can be thought as the superposition of a pendulum going along this axis plus a pendulum going along that axis. In the linear case, that is a very precise statement. The pendulum the linear pendulum, small amplitude pendulum in an elliptical trajectory is the superposition of motion along the minor axis and motion along the major axis. In a nonlinear problem, that is just an approximate statement. Because each swing, the swing along the minor axis takes a shorter time to complete one cycle than the swing along the major axis, which takes a longer time because the frequency decreases with increasing amplitude, right? So what happens then? If I set this initially in an elliptical motion, right? If I have this situation, I set it in what is in principle an elliptical motion. When this guy, when the long axis, or rather when the short axis completes a cycle, the long axis has not. Or viewed differently, when the long axis, or when the large amplitude component completes a cycle, the short amplitude component has already advanced farther into the ellipse. So what we are going to have is an ellipse that precesses. Okay? So, and this is where we see that forward precess. So I'm going to give an ellipse this orientation. Okay? So that is clearly an ellipse. Now notice that this ellipse forward precess. Okay? So it's moving, it's precessing this way because it takes a smaller amount of time to go along the small amplitude direction than along the large amplitude direction. Right? And it's very clear. The nonlinearity, while small, is very evident here because we can see the precession of that parabola, and it's forward precess. So I can do the opposite, okay? The precession would be in that direction. It's a forward precession still. So that ellipse is forward precessing because the motion along the minor axis takes a shorter amount of time than the motion along the major axis. Right? A dramatic effect however small. It gets amplified by virtue of the disproportional ratio of major to minor axis. So far, so good? This good? Okay. Now, we have analyzed this problem, the problem of a mass, say a harmonic or rather an oscillator that is nonlinear, but has no damping term and has no forcing term. So I think we are, yes.
The omega will go to infinite for a smaller than 0.
For alpha?
For alpha smaller than 0.
For alpha, yes. For alpha negative, as you increase the amplitude, the frequency increases. It's monotonic and increasing.
So we don't have still an oscillation.
We would have an oscillation, but the frequency gets looks like the mass gets stiffer with increasing amplitude. I mean, the spring gets stiffer with increasing amplitude.
Physically, what does it mean physically with an infinite omega?
Oh, well, to get an infinite omega, you would need an infinite amplitude.
Oh, yeah.
Right? Right. So, yeah, physically, you just have to get there. You just have to invest a lot of energy. Yeah. We're going to have, I'm going to show you a demo. Well, actually, I showed it to you yesterday. Now that I'm done with this, let me put it out of the table. And yesterday, I showed you this demo, which is related to your homework. These are stretch springs. Okay, obviously they are stretched from their equilibrium length, because the equilibrium length of these rubber bands is about this, right? The equilibrium length of such a rubber band is just that. So I'm stretching it. So by having a stretch rubber band, I have the second part of your problem, homework problem, where now there is a linear term to the frequency of to the forcing on for oscillations in this plane, in the vertical plane. Now this is a problem where increasing the amplitude increases the frequency, or rather reduces the period of oscillation. Larger amplitudes undergo a full cycle in a shortened amount of time than smaller amplitudes. Okay? It's not, in this particular case, timing it would be a difficult thing. It would be very hard. Okay? Because this is moving so fast, the timing would be difficult. So I'm gonna show you the effect that the frequency increases with amplitude with a different approach. And the way I'm gonna do it is I'm gonna first of all address the physical system that I have here. The system obviously has damping, right? It decays down to 0 amplitude eventually. And so I'm gonna incorporate damping. Notice that it takes a long time before it goes down to smaller amplitude. So the damping is a small term here. And I'm going to incorporate also in the equation, in the system that I'm going to analyze, I'm going to incorporate a forcing term. I'm forcing this system with, I'm going to be forcing that system with a vertical force due to this speaker going up and down. So let me show you where I'm going. And then we are going to analyze it, and then we're going to come back and see how our analysis does, okay, how well we did. So this is where I'm going. Just so you see the system, I have function generator. It just gives me a sinusoidal output, constant sinusoidal output. The output of this function generator goes into this audio amplifier, okay? And the audio amplifier, the output of the audio amplifier drives that speaker. I'm monitoring the whole thing with this meter here. So let me just drive it with a small amplitude, say, oops, not that, about that's too much, about there, okay? So I'm driving up and down, okay, and that is the response that I have. So what I want to do is analyze this particular system and analyze it under various amplitude conditions. What amplitude conditions? Meaning the amplitude of the drive, how much I turn the knob, right? If I turn it higher, well, it goes higher, it gets bigger, right? So there is a relationship between the driving force and the response amplitude. That relationship also does not only depend on the amplitude of the drive, but also depends on the frequency of the forcing, right? So notice that if I reduce the frequency, I'm slowly reducing the frequency. Notice that the amplitude goes down. The amplitude of the response goes down. I'm driving this at a fixed amplitude. This guy is going up and down with a fixed amplitude, but the frequency, as I change the frequency, the response amplitude changes. For a fixed amplitude of the drive, changing the frequency of the drive changes the amplitude of the response. That is what you've seen in the case of a driven damp harmonic oscillator. Yes? You've seen that in your mechanics course, right? Okay. So notice now I have a smaller response.
And that has to do with the resonance frequency.
Exactly. So if I move back up, let me move back up in frequency. So notice that the amplitude is going to increase as I move up in frequency. Yeah? You can see that? You can see the amplitude. I'm not changing the amplitude, I'm just changing the frequency.
Will the amplitude be max near the...
At resonance it will be max. So let's get there. I think I'm about there. Yes, because now the amplitude is going down. Okay, so I went like that. So from start with a low frequency, increase it. Well, let me do it from your point of view. Start with a low frequency, increase it, and then the amplitude went up and then went down. So I explore the response of the system near the resonant frequency of the system. Let's do that mathematically, and then let's do that for that nonlinear system. Okay? So this is what I want to do. I want to incorporate the effects of nonlinearity, damping, and forcing. So I'm going to incorporate damping. Yes, I have a two. I have a damping term, which I'm going to write as 2 lambda x dot. So this represents damping. The energy is dissipated at a rate proportional to lambda. So if I do the rate of change of the energy goes as lambda minus lambda times the energy. So that's the damping term. Then I have still my linear term, and then I'm going to have on this side of the equation, I'm going to keep this simple looking cubic term, is the simplest problem you can have, nonlinear problem you can have, a cubic nonlinearity. And then I'm going to put a forcing term, F. How am I doing that? F over M. F over M cosine omega t. Now, give me a little bit of tolerance here. I'm using I'm using omega here. This omega is not that omega, right? This omega here was the response, the frequency of oscillation of the free oscillator. Okay, so if you forgive me for my abuse of notation, I use omega to calculate the free response frequency. I'm going to use omega again, but not to mean that one, but to mean just the frequency of my drive. Is that okay? No confusions there? I could call it gamma, but unfortunately, I realized that later, after I was done with the notes, that I call it omega. So that omega there is not that omega that we just calculated. So, so you've seen this problem. The problem where we have a forcing term driving an oscillator that has damping. And you have found the solution for that problem. The response near resonance, if omega of the drive forcing, the frequency of the forcing term is close to the resonant frequency, so we write it like this. Okay, and for now, let's consider the case where alpha is equal to 0. So there is the system is linear. Okay. Then what happens is that the amplitude of the response, or the square of the amplitude of response, times epsilon square plus lambda square is equal to the square of the forcing amplitude divided by 4m square omega naught square. Let's see if this makes sense. At resonance, epsilon would be 0, right? When omega is equal to omega naught, epsilon is equal to 0. At resonance, the amplitude is is maximum, right? Because amplitude is f over 2m omega naught times 1 over epsilon square plus lambda square to the 1/2. When epsilon is 0, the amplitude is the maximum. At resonance, the amplitude is the maximum. So that result checks. Notice also that we have the problem when we don't incorporate dissipation, we have the unphysical result that the amplitude goes to infinity. Well, I mean, would be physical if we have a system that has no dissipation. But so when the at resonance, if there is no dissipation, the response amplitude goes to infinity, which is something that we talked about a couple of lectures ago. So this whole thing makes sense. Notice that the amplitude scales with drive, with the amplitude of the drive. We increase the amplitude of the drive for a fixed frequency, we get a larger response for a fixed frequency. So for a fixed amplitude, as we change the frequency of the drive, so if this would be omega naught, this is the response amplitude, and this is omega. As we change omega, at omega naught, we would have the maximum amplitude. Okay, and as we increase past, as we increase epsilon past the resonant frequency, the amplitude goes down. This result, by the way, is is only true about resonance. It's only true about resonance. It doesn't tell us how things behave, say, at zero frequency, at zero frequency of the drive. Okay? It doesn't tell us that. So there was an approximation in writing that result, so which I'm going to work in a little detail next time. So next time what I want to do is to work this problem so we get acquaintance with it, with the linear problem again, and then after I'm done with that, I'm going to just surprise you with the nonlinearity, okay? See what the nonlinearity does to this system, and then we do some demos with that, okay?